Good morning. In the last class, we discussed regarding checksum and calculation of checksum. Today's class, we're going to discuss regarding internet checksum. It is nothing different from the thing what we have discussed in the last class. So traditionally, internet checksum is used a 16-bit checksum. The sender and a receiver follow the steps which I am going to write it over here. The first, I'll talk regarding sender. The message in case of sender is divided into a 16-bit words. This is first step. So message is getting divided into a 16-bit words. Second step, the value of checksum is initially set to 0, like what we have seen in the previous example. Like the steps what we have used in the previous example, same steps will be listing over here by considering a 16-bit words. That's all. So checksum initially it is 0. So third step, all the words are added and using one's complement addition. Addition of all words. So that is using one's complement addition. Now all this thing will going to happen with 16-bit words. The example what we have discussed is for 4-bit words. For understanding reason we have taken a 4-bit word. And fourth step is the sum is complemented. And the last step here is the checksum is sent with the data. Sent to receiver with the data, with all the data. Okay, so these are the 5 steps which will going to happen at the sending side. Same way at a receiving side, the message and the checksum, first thing, that is at receiver. At receiver, first step, receive message and checksum along with checksum. This is first step. After receiving, the message is divided into 16-bit words. Then third step, add all the words. Using one's complement addition. It is using one's complement addition. The next step, complement the sum. The final step here is that if the value of checksum if it is equal to 0, message accepted, else reject, else rejected. These are the steps that will happen at the receiving side. So since the internet checksum, where we are dividing the whole words into a 16 message into a 16-bit words, so I have listed these steps. Or otherwise, whatever the calculation I have shown for 4-bit words, so the same thing, same kind of a calculation will be taken place with the 16-bit numbers. Okay, so same thing I will try to represent it in the flow diagram. Just now the steps what I have discussed, I'll try to represent that in the flow diagram. Okay, so this will be to start. Initially we'll start, I think it is visible. Then the next step, initially my sum is equal to 0. Then okay, is there any more words? More words? Yes, you perform this step. If it is yes, perform this. Sum is equal to sum plus next word. I'll write it as NW, next word. Yes, see, every time you need to add those 16-bit numbers. Fine. Till all the 16-bit numbers gets exhausted, you are performing this addition of those 16-bit numbers. So if it is no, moment that's all 16-bit numbers gets exhausted, you have to come out of it, and then you have to perform, say, that wrapping of sum. That is what is a part of one's complement addition. Okay, so where again I am going to make a decision box where, say, if leftmost sum is not 0, if it is not 0, then I mean leftmost sum is 0, this is a question mark, where if it is, say, no, sum is not 0, in that case what is to be done is, it is not visible, I feel, write it like this. Then I am going to write it as sum is equal to left sum plus right sum. So here we are talking of dividing the given value into two 16-bit numbers, and that sum, wrapping of sum, will going to be done over here. This is what is shown in 4-bit example. Yes, so you are performing this repeatedly till it gets reduced to a 16-bit. Yes, if it is yes, if it is 0, then come out of it, then perform checksum is equal to complement checksum is equal to complement, then last one, this is checksum is equal to truncate. Checksum is equal to truncate. So actually it is truncated checksum. That is what is the meaning of it. Then stop. Yes, this is what is the flow diagram representation of the steps what I have discussed. The major drawback in the traditional checksum calculation is that if two 16-bit items are transposed in transmission, the checksum cannot say catch this error. Say more than say two items get changed, it is difficult for say checksum to find the error. The major reason is that traditional checksum is not weighted. It is not weighted. So to overcome these particular problem, a newer methods has been proposed. So the newer method is, one of them is Fletcher's checksum, and second one is, the first one is Fletcher's checksum. The second one is Adler's checksum. We'll discuss regarding these two. Fine. So I'm not going to go into details of these discussions. Just I'll give you some highlights of it, and we'll try to attempt some examples on them. Fletcher checksum actually designed to weight each data items according to its position. Fletcher has proposed two algorithms. One is for 8-bit, another is for 16-bit. The first, we'll talk regarding 8-bit. In 8-bit, Fletcher calculates 8-bit data items and creates the 16-bit checksum. Okay, it is slightly different from the traditional checksum, in which our checksum value, we were dividing the data into a 16-bit words, and our checksum was also of a 16-bit word. But where in case of Fletcher's checksum of 8-bit version, in which we are say dividing say data into 8-bit words. Okay, so then we create a 16-bit checksum. And second version of Fletcher's algorithm is that where we are talking of dividing a data words into a 16-bit words, data into a 16-bit words, then it creates a checksum of 32-bit. So Fletcher's checksum, I'll write it in short FC. Two version, 8-bit, and second one is 16-bit. Fine. 16-bit words will going to be divided in, word size is 16-bit. Yes, and checksum size is 32-bit. But whereas in case of 8-bit checksum, so word size is 8-bit, checksum is 16 bits. This is what is the difference. So whatever the checksum we are getting, it is of 32-bit in case of Fletcher checksum 16-bit, and in case of 8-bit Fletcher checksum, the checksum size is 16 bits. There is no difference between say when it comes to the calculation. Calculation in both 8-bit and 16-bit remains same, but only the word size matters here. Now I will talk regarding a flowchart of say Fletcher's checksum for 8 bits. Okay, same thing is extended for 16-bit. To start with, say I'll talk regarding two variables, that is R and L, where R is a right 8-bit checksum and L is left 8-bit checksum, because total checksum size here is 16 bits. Yes, so left and right, so both are of 8 bits, 8 bits. So initially these checksum values are 0. This is what we are saying. So I initialized left 8-bit checksum equal to 0, right 8-bit checksum is equal to 0. Then I need to add a data words which are of the size 8 bits to start with. So I'll just use one decision box to check is there any more data. Okay, so initialized, and every data word gets added with a checksums. So first I'll just add with R. So I'll first update my R. R is equal to R plus DJ. J here indicates the ith data word. Initially it is, say, started with a first data word, second data word, and so on. So I'm talking regarding J. My message got divided into a J 8-bit words. Fine. So this gets added. So then I'll perform mod operation on it. Mod 256 is whose value is, if it is greater than, I'll rewrite it. R is equal to R plus DJ mod 256 yes, this is what happens over here. So then first we are adding the word and we are verifying whether it is greater than 8-bit or not. For that reason I am just talking of performing a mod operation over here. Then next we are talking of finding the left 8-bit. The procedure remains same, that is L is equal to, say, L plus R mod 256. So anything more than 256 gets added with a L. This is what is the meaning of it. So this addition continues. Okay, this loop will stay in the loop till all the data words gets added, and moment it gets added, yes, so no more data words then come out of this is a loop. Then I'll find out the checksum. Checksum, I'll write it as checksum is equal to C is equal to L into 256 plus R. This is how the checksum is going to be calculated. Then stop. Fine. So you are repeatedly adding a data words. Initially you are adding a data word with right side. So if a value gets, if it is more than 256, that means 8-bit will, with the 8-bit you will going to have a value up to 255. Fine. It's more than that, it will be added to a L. This is what is an idea used over here, and it gets repeatedly added, and by the time all the data words get exhausted, and if some exceeds more than 8 bits, so it will going to be represented in the 16 bits using this idea. Then we are calculating the checksum L into 256 plus R. Fine. So this is how we are performing the addition of it. I hope it's clear. So this is a Fletcher checksum. So right now I have shown you the flowchart of Fletcher. The same thing is extended to a 16-bit checksum. Now when it comes to a Adler checksum, this too remains, the idea used in Adler checksum also remains same as that of Fletcher, but there are few differences. I'll just list out those differences, and I will leave a flowchart creation for you only. It is a homework for you. Fine. So in Adler checksum is for, say, it is creating a 32-bit checksum like Fletcher checksum. Fletcher checksum also creates a 32-bit checksum when we are dividing the word into a 16-bit. Okay. So there is very little difference between 16-bit Fletcher checksum and Adler checksum. The three major differences I will list out over here. The first one, okay, so here the calculation is done on single bytes instead of 2 bytes at a time. I hope it is clear. So you are talking of byte by byte calculation. So you are talking of performing a calculation on single byte, not on 2 bytes like Fletcher checksum. Second, so that means single byte calculation. Second difference, the here mod. Okay, so when we perform R plus DJ or L plus R mod operation, whatever we perform, so that mod value, okay, so when it comes to a 16-bit, in case of Fletcher checksum, this value, it becomes 65,536, performing a mod with 65,536. But in case of Adler checksum, it is not 65,536, so it is 65,521, where 65,521 is a prime number. Okay, so because of that, it has been selected here. Okay, it may be R plus DJ mod this value, or it may be R plus L mod this value. Okay, so in both the cases we are talking of using a, say, this prime number 65,521 number instead of 65,536. The third difference is that, say, L is initialized to 1 instead of 0 in this case. So the L value here, it is initialized to a 0 because we are talking of using a prime number over here. This is what, these are the three differences between Adler checksum and Fletcher checksum. I hope it is clear. So till now we discussed some of the error detection techniques. So whether it may be a CRC or it may be internet checksum or Fletcher checksum or Adler checksum, in all these cases they are helping us to detect the errors. So there is no methodology specified here to correct the errors. They are only helping us to find the error present in the received data or not. So next I am going to discuss regarding a technique which helps us to correct the errors. Okay, so we'll discuss regarding, say, something known as, say, chunk interleaving technique. Chunk interleaving technique. Okay, so in chunk interleaving technique, basically it is for forward error correction technique, FEC, we call it as FEC. This is widely used in multimedia application. This is suitable for multimedia application. Once, say, after discussing forward error correction technique, why it is widely used in a multimedia technique, I'll explain it to you. Okay, so in this chunk interleaving technique, what we do is, the given packets, say I'll take 3 packets which are generated at a sending side, will going to be divided into a small units called as chunks. So we are not sending this packet as a whole directly to the receiver. So in forward error correction technique, what it suggests is, divide the generated packet into a small chunks. So for understanding reason, I am dividing my packets into 3 small chunks. So I will name them as, say, first packet I am going to name them as A1, A2, A3. These are the chunks of first packet. Second packet B1, B2, B3, and third packet C1, C2, C3. So while sending, while sending these packets, so what we do is, the sender, rather than sending a packet individually, what it will do is, it will create a new packet which will going to contain the chunks from, say, these different packets, that is A1, B1 and C1. So small chunks of every packet will going to be picked and they get converted into a single unit. So this will going to be transmitted like this. You are creating a chunks using packets using chunks of these packets. So second packet will going to be of the type A2, B2, C2, and third packet is A3, B3 and C3. So like this, a new packets will going to be created by using the chunks of the original packets. Now this arrangement is to overcome the problem of loss of packets. Say in case during the transmission, due to some error or some reasons, if one packet completely get lost, the lot of data will going to be lost. So by doing this type of arrangement, in case due to error or something, if one of the packet get lost, the loss of a data will going to be very less compared to the loss of one packet, because here we are losing a small data from each packet, small data from each packet. Okay, so this is how it is helping us to minimize the losses. So such a small loss of a data in multimedia applications is, say, tolerable. Say for example, if I assume that this packet is lost, instead of first one I'll assume that the second packet is lost. Okay, so I'll reconstruct the packet at a receiving side. How exactly it will go to look like? Say the packets, all these three packets, say out of this I assume that this is lost. If these two packets, if they reach the receiver in a safe way, the newly constructed packet at a receiving side will look like this. It will be A1, A3, A2 is lost, and it will be A3. The packet 1 will be like this, and packet 2 will be B1 and B3. B2 is lost, and packet 3 is C1 and C3, because C2 is also lost. So whatever the packets you are reconstructing at a receiving side will going to look like this. So now what we are achieving by doing so is the loss we are minimizing with respect to one packet. See, in this case I have divided my packet into 3 chunks. So how much I lost the data over here because of this loss of one packet? I lost, say, 1/3 of the total data. So the loss here is very less compared to that of losing one complete packet. So this will be very useful in multimedia application, because in multimedia application lot of video and audio content is transmitted. So such a small losses are tolerable in case of multimedia applications. So in multimedia application, this forward error correction technique is widely used. In this case, we are not asking a sender to resend any packets. So we are correcting ourselves. Receiver is correcting itself with these losses. Okay, so that is why we call it as a forward error correction technique. So there is one more way of correcting the loss of packet information. So where we are talking of combining a packet with two resolution packets. Okay, so normally in this case we create a duplicate of each packet, one with low resolution and another with high resolution or with the normal resolution. So we are talking of creating two packets. So we are creating a duplicate packets before sending them. So at sending side, any packet get generated with some particular resolution, we are creating a low resolution of that packet. So one with low resolution and another one with high resolution. Fine, we are creating two packets. One is with low resolution and another one is with high resolution. Okay, and when it comes to a sending of these packets, okay, so we are sending high resolution packet as it is, and normally every high resolution packet will going to carry one low resolution packet. Okay, say for example, I am talking regarding creating 3 packets. Okay, so we are talking of sending these high resolution packet. I'll write it as P1H. So the first packet will not going to carry any low resolution packet, but when it comes to a second packet will going to carry high resolution packet. Okay, the P2 of high resolution and P1 of low resolution. So low resolution packet of the previous packet will now go to be piggybacked with the current packet. So low resolution previous packet will now going to be piggybacked with high resolution current packet. Same way with P3. So P3 will going to carry P2 low resolution and its own high resolution. By chance, if we lose any one of these packets, I'll assume that if this packet is lost, P2 is lost. So we are getting P1 as it is. There is no problem of high resolution and it is not carrying anything with it. So no need to worry. But when it comes to a P2, the packet P2, if it is lost, so loss of P2 will going to be compensated using this low resolution packet. Now this loss will going to be compensated with low resolution and P3 will be of high resolution. Fine. So there are two high resolution packet, one low resolution packet. The loss of data, the loss of the P2 will going to be compensated now by using a low resolution of P2. So for this, what we need is, we need to create a lot of redundancy at sending side. So you need to create two packets, one with high resolution and another with low resolution. This is what is the redundancy what you are generating at a sending side. This is what you are paying for correcting the errors. This completes a error control technique. So tomorrow most probably we're going to attempt one quiz. Okay, so thereafter I'm going to post you one example on Fletcher checksum and Adler checksum. So you have to submit say its calculation through mail. So thank you.